All right. Today we're going to talk about 1b, which is propositions and truth values. So we will first get some definitions down. We'll define propositions and we'll define truth values, and then we will both define and apply some operations you can do with propositions, and we'll create some truth tables. Okay, so the first thing I want you to get down are these definitions. You can pause it here if you want to quickly write them down. So a proposition just makes a claim that has one of two values. It's either true or false, and it must have the structure of a complete sentence. So important parts here, it's either true or false, can be an assertion or a denial, and it must have the structure of a complete sentence. So this is what we call a binary system. The Greeks invented this, and any proposition has one of two possible truth values. It's either true or it's false, nothing in between. And a truth table is a table with a row for each possible set of truth values for the propositions being considered. And we'll make a couple of those today. So if you don't understand what that means, don't worry, you'll get an example. So here's a very simple example of a truth table. And the first operator we're using is called the negation. And so negation gives a proposition the opposite truth value of its original value. So we usually use letters to represent propositions. Sometimes we'll actually write them out in complete sentences. But for now, imagine that the letter P represents some assertion or some denial. Then P could either be true or false. So the negation of P would be not P. And the negation of P has the opposite truth value that P does. So when P is true, not P is false, and when P is false, not P is true. The symbol for negation is a tilde, or sometimes you can do this little kind of backwards 7. So if this is P, that is not P. Or sometimes you'll see it written like that. Both of those are acceptable. You can also just put the word not in front of it, but just wanted to tip you off to some of the formal notations. All right, so find the negation of the proposition. Amanda is the fastest runner on the team. Right, it's negation. So if we let that whole thing, that's a proposition, that's an assertion. It's asserting that Amanda is the fastest runner on the team. If I call that P, then not P would just be Amanda is not the fastest runner on the team. Okay, so pretty intuitive. It's just the opposite. Double negation. Double negation is exactly what it sounds like. You're negating the negation, which means the truth value is going to be the opposite of the negation, which now you're back to the truth value of the original proposition. So if P is true, not P is false, and not P is true again. So we're going to find out that these two are called logically equivalent because they have the same truth values at the same time. Meaning when P is true, not P is true, and when P is false, not P is false. All right, after reviewing data showing an association between low-level radiation and cancer among older workers at the Oak Ridge National Laboratory, a health scientist from the University of North Carolina at Chapel Hill was asked about the possibility of a similar association among younger workers at another national laboratory. He was quoted as saying, "My opinion is that it's unlikely that there is no association." Does the scientist think that there is an association between low-level radiation cancer among workers? So this is just a verbal example or real-life example of a double negative. So since he thinks it is unlikely that there is no association, these two things are going to kind of cancel each other out, right? It's a double negative. So the unlikely and the no association, that's a double negative that cancels itself out. So what he really thinks is that it's likely that there is an association. Okay. So moving on. So logical connectors are what they sound like. They're going to connect propositions. So they're almost like contractions in the logic world. So propositions are joined with logical connectors, and we're going to look at a couple of them, specifically three. We're going to look at the AND connector, the OR connector, and the if-then. All right, so we let P represent I won the game, and Q represents it was fun. So we can make new propositions out of that. I won the game and it was fun. I won the game or it was fun. If I won the game, then it was fun. So these have their own set of rules that we're going to look at. And you kind of have to let intuition go for a few of these and just understand, hey, these are the rules to the game. This is how it is. So AND statements. So two propositions connected using the AND, it's also called the conjunction, is true if and only if P and Q are both true at the same time. Otherwise, it's deemed false. So it's just the rule, right? So if P is Q and Q is true, then P and Q, that statement, it's a new proposition, is now true. There's a symbol that we use for it, like an upside down V or an upside down U. So you could have written that P and Q. But you'll see in all these other examples, they're not both true at the same time. And so the conclusion, the outcome is that P and Q is false. And that's just by the rule. If one of them's false, then P and Q is deemed false. All right, so let's look at the examples here. And for this one, we are going to take a general intuition for these propositions, meaning we're going to pretend we know the capital of France and Antarctica, etc. So the capital of France is Paris and Antarctica is cold. So we'll say the capital of France is Paris. Sure hope that's true. Antarctica is cold, also true. So we have a situation where a proposition is true and true, which tells us that the overall outcome will be true. And that equal sign with the 3 horizontal bars is a logical equivalence, which is just, it's different than numerical equivalence, right? We're not dealing with numbers here, we're dealing with statements. So logical equivalence, we use 3 horizontal lines. All right, the capital of France is Paris, and the capital of America is Madrid. So the capital of France is Paris is true. The capital of America is Madrid is false. So we have a situation where we have a new proposition that goes true and false. Now we know that the AND conjunction is only true if both sides are true. So this is false. All right, so 2 types of OR. OR can be interpreted in 2 distinct ways. Inclusive means either or both, and exclusive means one or the other, but not both. In logic, we assume that OR is inclusive unless told otherwise. So we will operate, for the most part, anytime you see OR, under the presumption that we are talking about an inclusive OR. Okay, so OR, also called a disjunction, just a fancy way of saying we made a new statement connecting propositions with OR. And so a disjunction is true unless P and Q are both false. All right, so it's almost like an inversion of the conjunction of and. And is only true if they're both true. OR is only false if they're both false. Meaning, if anything is true and it's an OR statement, then the overall truth value is true. So if P is true, Q is true, then P or Q is true. If P is true, Q is false, P or Q is true. False or true is true, and the only situation in which we get a false truth value is if they're both false. The symbol for or is just the V, capital V, or capital U. So this could have been written as P or Q. All right, and that's just the rule for or. So consider the statement, airplanes can fly or cows can read. Is it true? So we'll look at the two separate propositions. They're both assertions. Airplanes can fly. True. Cows can read. False. But we know that from our definition of disjunction, as long as one is true, then P or Q is true overall. So basically we can think of it this way. I have true or false. That gives me an overall true value. So I'd like you to pause it here and just try these couple of student examples, and we will talk about them in class. All right, so our final connector is the if-then statement. This is called conditionals. You might have worked with these a little bit in geometry. So they are another kind of weird one, and again, you just have to throw intuition out the window and just go, okay, this is the rule, this is how I'm going to operate with it. And here's the rule. This is called a conditional proposition or an implication. First of all, it goes if P then Q. P is called the hypothesis, Q is called the conclusion. So the way it works is that a conditional proposition or an implication will be true unless P is true and Q is false, meaning the only situation in which your conditional statement overall comes out as false is when your hypothesis is true and your conclusion is false. So you can see this second row. Hypothesis is true, conclusion is false. That's it. Otherwise, the whole thing is deemed as true. Okay? All right. So the other kind of difficult thing about this, the other difficult thing about conditional statements is that they can sometimes be written in not just if-then form. So if-then is a very straightforward way. If it's written that way, then you know that whatever P is the, if P then Q, P is the hypothesis, Q is the conclusion. But they can kind of be written in other equivalent formats. So another way of saying if P then Q is that P is sufficient for Q, P will lead to Q, P implies Q, and those are all at least in the same order as the original. You notice that Q follows P. Here are three other equivalent ways, and they're kind of written backwards. So if P then Q is equivalent to saying Q is necessary for P, Q if P, and Q whenever P. So it's really important. I would write these down. It's really important that you understand the connection between these phrases and the original conditional statement, and that you're able to take those phrases, anything written in any one of these 6 other forms, and rewrite them in an if-then form so that you can analyze the statement. So here's some actual examples of that, right? If P then Q. If it is raining, then I will bring an umbrella to work. So the hypothesis would be it is raining. And the conclusion would be I'll bring an umbrella to work. All right, so these are some variations on the conditional, the converse of that. So in the converse, we swap the hypothesis and the conclusion. So this one says, if I bring an umbrella to work, then it must be raining. And so the converse is if Q, then P. The inverse is just if you negate the hypothesis and negate the conclusion. So if not P, then not Q. So the inverse of that statement would be, if it is not raining, then I will not bring an umbrella to work. And finally, the contrapositive is, if not Q, then not P. So in that case, it's a combination of the converse and the inverse. You're kind of mixing them. So you're swapping the hypothesis and conclusion, and you're also negating them. So if I do not bring an umbrella to work, then it must not be raining. Okay. This is a huge truth table, and it shows logical equivalence. So two statements are logically equivalent if they share the same truth values. So this is if I look at two propositions, P and Q. And on the very far left, you can see that I've listed all possible ways their truth values could interact. So they could both be true at the same time. P could be true and Q could be false. P could be false and Q could be true. Or they could both be false at the same time. And that's all possible combinations of truth values for two propositions at the same time. Okay, so what next? Then we see the negation of each. So this is the negation for P, and that's the negation for Q. And you can see that the negation for P is the opposite of P at every value. Negation for Q is the opposite of Q at every value. All right, and then we see our logical connectors. So here we have the original conditional statement. If P, then Q. So remember that that conditional statement is only false if the hypothesis is false while the hypothesis is true while the conclusion is false. Then you can see the outcome is false overall. Otherwise, any other combination, you're getting a true outcome, and that's just by definition. All right, well, what happens when we look at the variations? If Q, then P. So now Q is the hypothesis and P is the conclusion. Well, again, we only get a false outcome overall when your hypothesis is true but your conclusion is false. And that only happens here, right? Because now Q is the hypothesis, so true, and P is the conclusion, so false. Any other time, you get a true outcome. All right, what about the inverse? Well, now we're looking at this. Not P is the hypothesis, and not Q is the conclusion. And so now we're looking at these two columns, right? And the only time a conditional statement comes out false is when the hypothesis is false. Sorry, the hypothesis is true, but the conclusion is false. So we take a look at this. When is the hypothesis true, but the conclusion false? Not P is true, not Q is false right there. Boom. What do you notice? You notice that the last two columns that we went over have the same truth values at the same time. So when I say that, I mean when we look at the columns, the rows have the same truth values. We call that logically equivalent. That means they mean the exact same thing from an argument's perspective. All right, last one, let's do the contrapositive. If not Q, then not P. So now not Q is my hypothesis and not P is my conclusion. This will only be false when our hypothesis is true, but our conclusion is false. And so now we're looking at not Q as our hypothesis, remember, and not P as our conclusion. So when is this one true and not P false? So true, false, we're only looking right here, right? And you can see that gives us a false outcome. And what you notice again is that these two columns have the same truth values at the same times, so they are also logically equivalent. So a conditional statement and its contrapositive are logically equivalent, and the converse and inverse of the conditional statement are logically equivalent. However, the original conditional statement is not logically equivalent to the converse or to the inverse, because they don't have the same truth values at the same time. First row, same. Second row, not the same, therefore not logically equivalent. All right. If a creature is a whale, then it is a mammal. Write its converse, inverse, and contrapositive, and evaluate the truth of each statement. Okay. Which statements are logically equivalent? All right, so I'm going to use some pausing here so that this isn't so long. So this is the original statement where, if a creature is a whale, then it's a mammal. So a creature is a whale is the hypothesis. It is a mammal is the conclusion. So let's start with the converse. So for the converse, all I need to do is swap the order of the hypothesis and conclusion. So I'll say, if a creature is a mammal, then it is a whale. Now the original statement overall is true. What about this one? Well, all you need to do to prove a conditional statement false is give a counterexample. And so I could say, if a creature is a mammal, humans, so that would make the hypothesis true, then it is a whale. Nope, humans aren't whales, so the conclusion is false. And we know that when the hypothesis is true and the conclusion is false in an implication, we get a false overall outcome. All right, so now let's start with the inverse. So for this one, I just need to negate. I need to keep the original hypothesis and conclusion in the same order, but negate each one. All right, so for this one, I said, if a creature is not a whale, then it is not a mammal. So I just negated both. All right, so let's evaluate this. Let's come up with a counterexample. Once again, human. So let's see how that works with our propositions. Creature is not a whale. That's true. A human is not a whale. Then it is not a mammal. That's false because a human is a mammal. So here we have true implies false, and that's the only way that a conditional statement can be false. So my outcome is false. All right, last, let's do the contrapositive. So here we're both going to flip the hypothesis and conclusion and then negate them. So I'm going to flip the order and also negate them. All right, so once again, we can analyze this by coming up with an example to satisfy our hypothesis. So a creature that's not a mammal, let's say a lizard. So if a creature is not a mammal, true, then it is not a whale. True, and we know that true implies true, gives us true in a conditional statement. So this one overall will end up being true, which will match our original statement, which was true. And you can see logical equivalence there, right? The original statement is true, so the contrapositive must also be true. The converse and inverse are going to have opposite truth values of that original statement, so they are both false, and they're also logically equivalent to each other. All right. Here's a student example. Go ahead and make me a truth table for the following statement. So since we have only one proposition, which is Q, you're only going to have two possible truth values for it. You're going to have true or false. I'll let you take a shot at this and we'll go over it in class.